Hello everyone, my name is Benjamin Gansa and I'm making this presentation as part of the article review for geospatial data structures. And in this, I reviewed the paper Rapid DEM, that's Rapid Topographic Update through Satellite Change Detection and Data Fusion. Rapid urbanization causes significant topographic changes, but DEMs are rarely updated due to cost and then time constraint. And these outdated elevation models also become unreliable for hydrological and then urban planning models. So in order to fix this, usually what researchers do or practitioners do is an existing DEM that was created by maybe satellite data, okay, but then if you are going to do another DEM, does it mean that you have to do it for the whole region? What about the places that they did not see any kind of change? Okay, so instead of flying the whole region to update the DEM, what if you use a prioritized approach where we target areas where we assume or predict that there has been significant change, and that's the priority approach that this study tends to use. So the aim was to provide a rapid topographic update through satellite change detection and UAS data fusion. And objectives included detect and then prioritize areas of potential topographic change, generate high resolution DEMs using targeted surveys, and then seamlessly fuse UAS DEM and then existing elevation data. So the framework that the study adopted was to first develop a land cover land use change map for a prior and then after um, images, and the random forest method was algorithm was applied here. Secondly, was to prioritize the topographic change based on using priority queue. Third was to collect data using UAS and then generate a new DEM using SFM approach, and then fuse this DEM with the existing DEM using the blending based distance approach or algorithm. And then the various data sources included planet 3-meter multispectral imagery, labels from OpenStreetMap, the UAS imagery, and then USGS LiDAR-based DEM. So let's go to, as I mentioned, for the purpose of this study, I'm concentrating on the priority queue algorithm that was used. And then the purpose of implementing this algorithm was to the fact that you are going to identify areas where there has been change and you believe the change is significant or is prioritized, okay? And then this is based on the fact that we will compare before and after a land cover image of the area, assign a priority score, compute a weight for the score, and then normalize the score on a Likert scale. And then the Likert scale is from 0 to 7. And 0 means area where there's no priority or there's not any change that we are interested in. And then 7 means area with the highest priority, such as like from an area that changed from forest to a barren area or a building, meaning that there was significant disturbance in the topography. And then the algorithm was implemented in this way. The priority change map was computed, that's the before and after classification, to assign numeric score to each change, and also conduct the change objects, compute the change objects, that's group pixels into change based on or using connected component labeling, and then compute the mean object priority change, which calculates the average priority change within each object, and the change object area, that's the total size of a particular change within a particular object. And then we score this, and then we normalize the score, okay, using the normalization method. And then after that, we export this raster data to polygons and superimpose on the image. So after developing this framework, they implemented it on the Walnut Creek watershed as a case study. And in addition to the implementation of the algorithm, they collected US data and then generated DEM using SFM MVS approach. And the purpose for this DEM was to be able to quantify the change that has happened. And after getting the new change based on the UASDEM, they fused it or blend it with the existing USGS LiDAR DEM in order to get an updated DEM of the area. So this is the result of the land cover land use change, and it shows the before image, which was within 2018, and then the after image in 2020. And this is also the priority queue land cover map. The top left shows the areas where there is change and then no change. And then for the change area, you can see that some of the areas are big, whilst others are small. And this area was superimposed on the automosaic generated from the DEM, UASDEM. So this is an exemplary priority map area which has been ranked based on the change. And then you can see that bigger areas of change are highly ranked compared to smaller areas. And also the priority also include, for example, from clearing of forest to the construction of new buildings. So after that, the areas where there has been change is also surveyed using the UAS, and the new DEM of the area is created, DTM, both DTM and then the DEM. So the DSM is also created, and then this DSM is fused on the existing LiDAR DEM of the area, so that at the end of the day, you will get a seamless surface of an updated area. And this surface, as can be seen, has no visible flaw in terms of the hydrological flow. So at the end of the day, they have been able to update the existing DEM of the area to a new one, which is more recent, and then which reflects what is in the landscape. And indeed, as it can be seen in the map, there is no visible flow fault in the hydrological area. In terms of contribution, this study is innovative, and in particular, the adoption of the priority queue helped to focus the US flight on areas where there has been change, okay, rather than flying the whole area, which will not be cost effective. And also, the study did the real world implementation of the Walnut Creek area watershed, and also the implementation was done. The workflow is based on open source software, which can be easily reproducible. Nonetheless, there are some limitations, okay? For example, the false positive from the priority key was high, which amounted to about 53% of the identified area were just coming from noise. Okay, so that is something that need to be worked on and then improved, because 53% false positive can also be not cost effective visiting all these areas. And other things like introduction of deep learning and then comparison with other areas too can be done. So this is the reference for my study, and then I say thank you.